Yeah, fluid structure. Yeah. Okay. Are they related via resonance?
Yes.
What was that face? Andrew's wrong. Yes, freaking finally. Why are they not related via resonance? That little hydrogen has changed locations. Not allowed to move atoms. So these are definitely not resonant structures. Okay. When it comes to this question, both are acceptable. I didn't even process the best. So I would have accepted both of these. Which one was I intending students to draw?
The one on the left.
Ooh, the one on the left. Why the one on the left? This is a really hard question to be able to answer this, by the way.
In the ring, they're all sp2. So for every sp2, you have a p orbital that can allow for electrons to move in between them.
There we go. The blue structure was the one that I was aiming for because you've got sp2 hybridization on each of those carbons, or said another way, you can do resonance within that structure. That resonance alternates those pi bonds all the way around the ring. That resonance incredibly stabilizes the overall molecule. That was the intended structure to be drawn. Then somebody drew the structure in red, and I was like, wrong. And then I went, wait a second. Damn it. And I had to double back through and address that there were other ways to potentially set that up.
So it's definitely right.
What's that? Yep, both of them were. So that one person had this big, massive, like, cross through it with me saying wrong, and then like, oops, sorry, you're okay. Okay, so both of those are acceptable as far as I'm concerned. Okay, it's starting to push into content that you don't necessarily know. When we look at the sulfate, because I asked this one a whole bunch for a bunch of the different groups. So a couple things come out. Number one, if we watch how I just went through and drew this, you'll note, did I follow any of the steps that I told you to follow? No, because I know the answer. That's why I can draw it that fast. Okay? One of the things that you have to be very careful with when you go through and draw these is, do you actually know the answer? Whoops. If you do, yeah, go ahead, write out the answer. But the odds that you actually know the answer is probably pretty slim. I would recommend you follow some work process so that you could go through and evaluate it. And what I saw at least one group do is they drew this out and then they went back and tried to show a whole bunch of work. Okay? Again, what I see isn't going to be your stepwise process. What I'm just going to see is the end result where it's all there. So I wouldn't know that, except I get to watch you do it right now and be like, why are you doing that? Okay? And that's okay. But that's the process we want to think through. When we go through to set up our system, our step one is to figure out all the valence electrons. Once we know all the electrons, we can then start dumping them into our structure. And when we dump them into our structure, this isn't where we should initially get. Where we initially get is with the sulfur with just its octet satisfied. And we end up with this structure. More or less, I'm being lazy with the electrons. Okay? Gen Chem goes, oh, we just put on brackets and say it's -2. That's lazy. We're better than that. And by we, I mean you. You are better than that. So be better than that. What do? We associate charge to our atoms. When we go through and associate the charge to the atoms, we'll find out all of these oxygens would be a -1 charge, and that sulfur would be a +2. That's a whole hell of a lot of charge. And when we draw out Lewis structure, octet is first and foremost our primary goal. The next goal is minimize charge. Okay? And in this system, I've got a whole heck of a lot of charge that if I shift some electrons around, I can minimize that charge. To get to the red drawing, what I could do is remove a pair of electrons from the top and bottom, and I could place those pair of electrons in the space between the sulfur and the oxygen, and I've now minimized the charge on those atoms. I can't move any more electrons around to minimize charge, which is a good thing because the formula was -2, so my overall structure should be a -2. Kind of makes sense? We good? Cool. The next question's there. I'm going to scroll a little bit. but you should still be able to read everything. Should I read it to you? Sure, why not? A compound with a molecular formula of that has a melting point of 203. The compound is soluble in water but not in diethyl ether. Based on your knowledge of organic structure and physical properties, is the compound most stable in its ionic or its covalent form? Justify your answer. Okay. Where we're going to start is the most common answer. This one's it because polar covalent is a more stable bond than ionic. Incredibly common. Physical properties. In that explanation, do we touch on the concept of physical properties at all? No. Okay. It says melting point of 203. Did I touch on the melting point of 203? No. Okay. Talks about solubility in water. Did I talk about that? No. So why the hell was all of that information given if that was my answer? Maybe it was just to mislead me. Okay? So you could leave that, move on, and hope for the best. Okay? Or you could come back and say, well, why would that other information be there? Okay? There's a reason the question very specifically says physical properties. Okay? You got people at the table. It's not worth drawing anything up on the boards, but you got people at the table. Talk through it. Words out of your mouth. Talk about it. Okay? So I heard a lot of people still jump at, well, it's this one because ionic bonds are unstable, there's less charge. That's great. That's fantastic. Okay, I love it. Did you address physical properties? Still no. Okay? You could be, well, they're distractors. They could be distractors. That's possible. Okay? But let's at least attempt to dig into them. Which one do you want to look at? Melting point or solubility? Okay, melting point. So the melting point is 203 degrees Celsius. What do we look at with melting point? Okay, forces. How do the forces affect our melting point? Stronger force, it's okay, is a higher melting point. Okay, is 203 a high melting point? Okay, if that's a high melting point, what does that suggest our force is? That should be a strong force. What forces do I have in my molecules? We've got dipole-dipole and London dispersion forces. I'll accept that. What's the other compound? It's ionic. How do we know it's ionic? Because there's a cation and an anion. That's with our ions. That's ionic. Okay? Which of those is the stronger force? Ionic. So based off of your melting point, which compound do you think is the correct structure? The ionic one. We have direct evidence that would suggest that that one is correct. And maybe you're like, well, 203 isn't very high. High is a relative term. That can be a challenging one to nuance. Okay, but based off of our experience with our melting points, that's a little up there. Okay? So we might be saying ionic, but maybe that isn't strong enough, so there's a little question mark. Was there more information given? Yeah, we talked about solubility. What is solubility?
Dissolve like forces.
We got our like dissolves like, and I'm going to be super lazy and leave the forces off, but it's all based off of forces. So if I go through and look at this, water has what force? Hydrogen bonding. And if I'm talking about like forces, it might be useful to know what all my forces are. What are all my forces?
Electrostatic.
You had to say that one.
Uh,
Electrostatic, also known as ionic.
yeah.
Okay, what else? Hydrogen bonding. Dipole, and induced dipole. It's two. Man. Induced dipole, yes, a more appropriate definition than London dispersion. So those are all my forces. If I have hydrogen bonding, what forces would be similar to it? Electrostatic and dipole. It's dead in the middle. If I just had LDF forces, I'd be like, nope, not that one. So I go back to my compounds, electrostatic. That was also known as ionic. Okay, so the solubility in water is suggesting that it could be ionic. It also suggests, unfortunately, it could be the dipole-dipole. Okay, so that's not a perfect fix. Did it end with the solubility in water? No. What did it also bring in? Okay, it brought in diethyl ether. Do you know the structure for diethyl ether? Okay, so for the people saying, "Oh, what did I?" Keep your mouth shut. Do you know the structure for diethyl ether? Okay, if you don't, how do you fix this? Wow, you're just burying your classmates. I mean, it's fair-ish. If you don't, what should you do? Raise your hand and ask. And you could draw it. The only reason you can draw it is because you knew how to name it. Okay? And if you were weak with naming, that's going to be a problem. Raise your hand and be like, dude, I don't know diethyl ether. Please help me out. You'll be like, okay, fair enough. There's diethyl ether. Okay? And for people like, I knew what it was. I didn't care about you. Okay? There's structure of diethyl ether. What force are we going to get out of diethyl ether? Dipole-dipole. What things are similar to dipole-dipole? Hydrogen bonding, London dispersion. Except this says not soluble. So diethyl ether has the potential to dissolve hydrogen bonding, dipole-dipole, and London dispersion. But it says not soluble. Which one of these things is not like the other? Electrostatic. So based off the diethyl ether, we should be looking at the electrostatic one. Which one has electrostatic? The ionic. Our melting point leaned heavily ionic. Okay? Solubility with the hydrogen bonding was a bit tricky. Would have been nice if I'd color-coded it a little bit better. But it would do both of those. The electrostatic, or then our diethyl ether, is pretty much the nail in the coffin. Says it's got to be the one that's ionic. Okay? And this introduces an interesting dilemma, because where we initially started was all structures want to minimize charge. So therefore, it must be a covalent bond. Yes, all structures want to minimize charge. How they go about minimizing it and minimizing which charge becomes really, really important. So let's erase everything. Can I erase everything? There's a special feature hidden within that nasty, positively charged species. What's that special feature hidden within it?
Carbon has a charge.
That carbon has a charge. Do more.
Uh,
Not you.
okay.
Sorry. Sorry, not sorry. Do more. I want to know more about that carbon. So, Karina, good job, but you answered the wrong question. I want to know more about that carbon. It has one hydrogen. Yeah, it does have a hydrogen chilling on it. Say that again. It's sp2, which means what's left over? A p orbital. And what could we potentially put into a p orbital? Electrons. Electrons that we could get by doing, now you can jump in, Karina. Resonance. Guess what? This molecule allows for resonance all the way around that when I kick that bromine off. That resonance is such a strong stabilizing factor that for this particular molecule, it ejects that bromine almost instantaneously. Did you need to know that? No, not at all. Okay. What you needed to know was process the information you have at hand, okay, to answer the question. Use that context to help you navigate. And yes, it is possible it's a distractor, but don't ignore it offhand and say, well, I think it's a distractor, therefore I'm going to ignore it. Evaluate it a little bit and be like, oh, dang, well, depending on how I evaluate that, that could actually be a legitimate piece of information. Let's lean into it a little bit.
So, for your test, is it all right if we just draw instead of
What do you-
write a whole paragraph about why.
Oh,
What do
for
you
this?
prefer? Like, would I have to write down, oh, it can perform resonance or whatever?
Oh no, I can do this.
So I think it's just easier to like do something like that.
Is that a complete sentence? Some people are laughing like, oh God. No. It doesn't say complete sentences, it says justify your answer. Have I justified the answer? Yeah. I was able to justify it with a bunch of colors. Do you have a bunch of colors?
I got a circle thing.
Okay, so that's how you would have to try and navigate that. Sometimes because you are limited in your color choice, you would have to add a little bit more language behind that. Okay, at least when it came to the solubility one. With the melting point one, you didn't need a color. You say that's a high melting point, high force. That's ionic. That satisfies.
If this question is 3 points and you only pointed out the melting point stuff, would you not get full points if you don't?
It's a good question. How do we divide up the points?
Correct answer.
Do we get a correct answer?
Yeah.
Did you point out the melting point? Did you address the solubility? 3 points. 1, 2, 3. You just circle the answer? Did you circle the right one? Lucky you. Have a point. Okay? You give me no explanation? Did you provide an explanation but not tell me what it was leading to? I don't know how you pulled that one off, but good job. Okay? That's only going to be 1 point. Okay? So yes, I do assign partial credit. And yes, if you're looking at those numbers are chosen with intent. I'm usually looking for certain pieces of information. Is that a hint?
Kind of. What if you didn't gauge what if you said 203 was not high? What you said?
Yeah.
It wasn't a strong force.
Okay. You looked at the melting point and you said 203 was not high. What did you draw as your conclusion then? That the left one was. Are you right? Hell no. Is your logic consistent? Yeah. So you'll get me crossing it all out and mean this is wrong. Here's 2 points. Make sense?
Yeah. So you get 2 points.
You provided an answer and you provided a context. Your context sucked, but you know. You have to be real clear on that. You have to be like 203 is not a strong or a high melting point. That means it's going to be a weaker force. So you have to convince me of your wrongness. Okay. How far down that rabbit hole did you actually push?
Is the test gonna be framed like this, where it's like a quarter short answers, 2/3 short answers, the
Yes.
rest of the choice? Okay.
Points wise, yeah, that framed that way. It's 5 to I don't know. I usually say 5, but then I remember that I've only promised 5 to the 130 students. For OChem, I don't think I've promised a number. Questions about that one? Okay, cool. Negative carbons. You got friends? Talk to them. So now we're looking at it. What do we see? So within this, it's going to come down to, again, your comfort with those drawings. What you see within them, what you don't see, all of those individual pieces. The specs quizzes have hopefully helped with that so that you should be able to see some stuff a little bit more readily, like implied hydrogens. Okay? And in particular, the lone pair on that carbon being negative. Right? We could go through and populate the same thing on the other carbon. And the lone pair and that hydrogen. Here we're going to have to get a little bit more aggressive and go to that one. Right? We're concerned about the negative carbon, so I'm concerned about what that negative can do. Well, that negative is ultimately due to a lone pair of electrons. What can lone pair electrons do? They can potentially move through a process known as resonance. So what we should try and do is see, can I move those electrons? Could I move those electrons down? And hopefully what we would see is that that move is going to be illegal because the octet is exceeded. I can use that information to my skill set if I want and realize that I would have to draw an arrow back on it, which means I would draw an arrow back there. The net result is no resonance. So I can't move those electrons. I could try to equally move them out to the hydrogens. Hopefully you'll note that the exact same issue builds up. We can't move them to the hydrogens. If we move to the blue structure, I can move it down. Okay, same system. I'm going to move those electrons down. We're going to attempt to see how I can move them. I would end up with this drawing. This drawing encounters a similar issue. We've exceeded the octet. So I've drawn an invalid structure again. But with this invalid structure, I can now ask the question, is there something else I can do to fix this? Yeah, I can move a pi bond. I can move the pi bond that I just made, which means nothing happens, or I have a second pi bond to move. And if I'm going to move that second pi bond, I need those instructions drawn on my original structure, a valid structure. Right? And now I encounter an interesting dilemma. Do I do the orange arrow? I don't think I've ever used pink. Let's use pink. Or the pink arrow.
Pink arrow.
Right? And it's kind of, I wouldn't argue, really a trick question per se, but it doesn't matter which one you use. Right? And for those people, but you would exceed the octet if you did the orange one. You're right. So you would have to add another curved arrow. And so eventually what you would end up doing if we followed that orange path is putting those electrons onto an atom at the end of the chain out here. If we followed the pink path, pink as a color shows up pretty nice. I should use it more often. I would put the negative charge there. What does this mean for me? That there's resonance structures possible. What do those resonance structures do to the negative charge? It distributes it across the molecule. So what becomes the effective negative charge on any one atom? Less, and depending on how you want to look at it, less negative. Let's go with that. Okay. We're concerned about the carbon in that structure, so let's erase all those pieces. Let's look at the charge on that carbon. Well, if we call it the blue structure, what's the charge on that carbon? -1. Okay. Is the blue structure the correct structure? And if that one's puzzling you, that's because you're disconnecting on what resonance is. If I have resonance, guess what I have to do? Evaluate all of my equivalent resonance structures. Blue, pink, and orange are all equivalent, which means all of them must be factored into my discussion on deciding the charge, which means if I'm going to figure out the charge, it's the average charge for that carbon across all those molecules. What was the charge in the blue one? -1. What's the charge in the pink one?
-1.
What's the charge on the carbon in the pink one?
0.
It's 0. I've distributed that negative charge to a different carbon. What's the negative charge in the orange one? And as I calculate an average, I add up all the charges and then I divide by the total number of things. In this case was 3. The negative charge on that blue carbon is -1/3. Which one is more negative? A -1/3 or a 1? The 1 is more negative. Which means in this particular case, the most negative carbon is the one on the left. Why? Because the blue one has resonance. Why was the ionic structure more stable?
Because it had resonance.
Oh. Why did we go through and exceed the octet on the sulfur?
For charges.
To minimize charge. And how do we minimize the charge? Through moving electrons, also known as?
Resonance.
Ooh. It's almost like resonance is this thing that's going to constantly underpin almost everything we look at, because it is. That's why it's so important to really push and understand what's going on within our resonance structures. I just deleted everything.
I was just gonna ask, like, for your explanation, like, would it still be wrong if you just because, but like, because the blue had more, like, had resonance?
I would get grumpy, but I'd accept it. Because I'd like to see that you're showing me resonance. Yeah. I would like to at least see a curved arrow proving to me that you're understanding it. Because you could just look at it and be like, well, Mike said resonance was the answer to almost everything. I don't know what shit all this answer is, but I'm going to circle one and I'm going to write resonance and hope he gives me points. That's why I'm going to get grumpy. Okay? So if you instead show a curved arrow and write resonance and circle the other one, I go, okay, I get it. Does that make sense? I like this next question a lot. It's a challenging question, though. And it's entirely made up. Like, this could be completely wrong, for the record. This is a different question. Never mind. I might be thinking of the question that's actually on your exam. Exciting. So, being able to recognize where partial charge is located in a structure becomes critical to predicting the relative reactivity of molecules. So we've got this structure here. What I want you to go through and do is identify two atoms that would be most likely to interact with a negative particle. What would I expect the charge to be on an atom that would interact with a negative particle? Positive. So what are you being asked to find? A positive. So, find the positive. Talk to the people around you, see what you come up with. Okay, deep breath. Because I think we're starting to pull some weird stuff out of a hat here. What's going to generate a positive charge? Why would anything become positive? Something has taken something away from that positive. What was taken away from that positive?
Electrons.
Electrons. So if electrons were taken away, we're now looking at two atoms. One of them became positive, the other one took electrons away. Do we have any kind of physical description or definition for an atom that has the ability to take electrons away from another atom? Electronegativity. So if electronegativity isn't crossing your mind, you got a problem. That's where partial charges come from. It's the difference in electronegativity between those atoms. It's actually one of the specs quizzes too. Okay? So when we go through to try and find a positive, the very first thing we should do is not actually find the positive, but find the electronegative. Because the electronegative is going to start pulling electrons away. So I look at that and I see carbons, oxygens, and hydrogens. Which one's most electronegative? Oxygen. Good. Nice speed. So what's that oxygen going to do to the electrons around it? It's going to pull them towards it. And as it pulls those electrons towards it, the oxygen starts to become partially negative. What happens to the atom on the receiving end of that? Becomes partially positive. Okay? That's what we would refer to as an inductive effect. We'll talk about that more later. But all we're talking about is just a difference in electronegativity. That's it. That's all we described. But as we described it, note that I drew an arrow, right? What am I drawing that arrow on top of? A pi bond. And what do pi bonds have the ability to do?
Jump atom.
Move via resonance. So I could leverage that resonance of my arrow to immediately go through and say negative. That carbon is positive. Yeah. Is it formally positive? There's a good catch-all on that. You're like, in that structure it is, but remember it's resonance, which means you can't look at one structure, you have to look at both. And in the process of looking at both, the carbon is not formally positive, it's partially positive. It's a real strong partial positive because we have a resonance structure where the electrons have been taken away. Cool. So now I've got a resonance structure, yippee doo-dah, what do I do with that? Well, what do we do with any resonance structure? Look for more. Is there a question there? In looking for more, what am I allowed to move? Lone pairs or pi bonds. The lone pair I already played with. I don't have any other choice, so what I'm going to do is tackle the other pi bond. Can I slide that pi bond across? Yes, absolutely I can slide that pi bond across, and when I do so, what happens? That carbon is no longer positive. There's my new bond. We'll call it orange. True, so I've lost the positive carbon, but at the same time, what have I gained? Another positive carbon. What were you asked to do?
Find two carbons of that bond.
Find two atoms. I did not say carbon. Find two atoms that would be positive. What have you just found?
Two atoms.
Two atoms. Do you have an explanation for why those atoms are positive?
Yeah.
Yeah, that's actually already drawn there. That's what the beauty of drawing mechanistic curved arrows. The phrase mechanistic doesn't mean anything to you yet, but showing curved arrows for resonance, it's already an explanation. Okay? You now have two positives. Okay? And then one of the things that seems to catch everybody on this is they look at it and says, oh, there's three. So I'm going to stare at it longer. Did you answer the question?
Yeah.
Yes. Move the hell on. Okay? There's a reason it's extra credit. It's because it's not obvious. Okay? So move on and hope for the best. You got time later, come back to it. Which means, ta-da, time later, we have it. Now we get to come back to it. What other atom could possibly be positive?
The one between
The one between.
the one between the pi bond, that one. Yeah.
That carbon, turns out, is actually very negative. Okay? And you might wonder about that one because you don't see it in each of these cases. But if we overlay this system, we have a negative followed by what's next? A positive followed by what's next? A negative followed by what's next? A positive. Guess what? Our charges will alternate as you navigate through a structure. Okay? So that can be a useful thing to key in on to help you kind of push through that system. That carbon that you're pointing at more than likely actually has a large amount of electron density. And for this particular molecule, when we talk about how it chemically reacts, it's negative. Okay? So there's a good guess, like a double bonds, right? Technically, the answer isn't 3 valid answers. It's technically 5. I would argue it's 3 because it's 3 types. That hydrogen is actually very positive. Why is it very positive? So you could run the patterns that we just talked through. It's connected to a negative carbon. Why is that carbon negative? What do I want to do with those electrons? How about I share them with that formal positive right next to it? That hydrogen is what is known as acidic. How acidic? It's the same acidity as water. We're talking about the bond strength up between a carbon and a hydrogen being the exact same as the bond strength between hydrogen and oxygen. That's pretty wicked crazy. Okay, where are the other 2? 1, 2. Those hydrogens are very acidic due to this drive inductively to try to stabilize that positive. That drive isn't through resonance, which means it's very hard to pick up and see. So don't sit there spinning your wheels on extra credit. Move forward. If you get time, double back and try and poke at something. Make sense? And if you hear me grumble as I walk by you, I could just be clearing my throat. But more than likely, it's because I feel like you're staring at something for too long and you need to move the hell on. Make sense? I can just clear my throat for the record. Okay. This one's just identifying things, identifying atoms and all that kind of fun stuff. Is this something you want me to walk through and do? No? Okay, fine with that. Oh, this is my question. So maybe it's not on the exam. I love this question. What we're looking at here is a very short sequence of an amino acid. Okay? And when we look at amino acids, they've been studied a lot. And they went through and they studied, or someone went through and studied the common bond angles or rotations about those two spots. Psi and Phi? I don't know. Those two Greek letters. Okay? And what they noticed was a whole bunch of cool stuff, that when those angles hit certain things, we got different shapes came out of the molecule. Okay? The extended structure. So it's neat, it's fascinating, it's known as the Ramachandran angles, but you don't care. Okay? Where I want you to care is that there's another bond angle. We could have looked at this label X. Why was the label X likely not discussed? We got blue, we got orange, and we'll call it red. You can stew on it. Talk to the people around you. See what you think. So, what is different between red, blue, and orange? And one of the statements that got called out was a good statement, though it's missing some information. They said, the difference is between sigma and pi. Right? As a blanket statement, sigma and pi is a phenomenal idea because we're talking about here bond rotations. And what do we know is the difference between sigma and pi? Sigma can rotate, pi cannot. That's that p orbital overlap. Okay? But when I look at this, red, blue, orange, they're all sigma. They're all sigma until I do what? Do resonance. And as soon as I do that resonance, what happens to the ability to rotate? I can't rotate anymore. And remember that when we're talking about these structures, neither one of these is correct, which means at all times there's electron density shuttling back and forth in there, which really just means there's only two possible configurations around bond X. That's it. And if there's only two possible configurations, that's not going to dictate the wild range of possible shapes that I get out of it. You're like, well, can I do resonance the other direction? I don't know, try it. And what you should be able to prove is that no, you can only do the resonance from that nitrogen over towards that carbonyl. And there is no other resonance systems that you can run through the blue bond or the orange bond, which means those are left freely as sigma bonds, and those sigma bonds now have a wild range of possible rotation states. And then the fun question is, why the hell did I think of this question? I have no flipping clue. It came out of nowhere. Actually, that's a lie. I do know where it came from. It came from when I was teaching biochem. Let's just be glad I'm not doing that anymore.
But this is a question on nuclear.
What?
A similar question to this one is on nuclear.
Maybe. I actually don't know. It wasn't there initially, so I thought maybe that's where it was. But no, it turned out it was here. So maybe it won't be on the exam. So cool.
The majority of this has been resonance. Do you know what resonance is?
Yes.
All right.
Right, and that's an important observation that was made at least at one table. The majority of our answers have come through and been resonance, which means, do you think resonance is an important concept?
Maybe.
Yeah. You should probably make sure that you have some at least passing comfort with it. And when you look at a question, you can look at it and be like, ooh, I don't know how to answer this. Resonance. That should be your reflex. Doesn't always work, but that's a really good reflex to pick up. Okay. So we talked a little bit about solvents, and we'll talk a whole lot more about them when we move into Unit 3. I don't know why I said after Unit 2. That's kind of dumb. I should have just said Unit 3. So we've got a chemical reaction happening above. Which solvent do you think would be best to stabilize the cation? So for this chemical reaction to work, the critical step is that first one. We need that cation to be as stable as humanly possible. So what solvent would do the best job of stabilizing that cation? And if you go through and look, there's a whole bunch of different answers, right? Does that mean there's only one right answer? No, this is fun. You could circle a bunch of different answers. All I need you just to do is circle one. So what do you think you need to stabilize a cation? An anion. Do any of your answers have an anion?
Two.
Try again. An anion would be a negative charge. Do you see a negative charge? No, there is no anion. So what's next best to stabilize that positive charge? A partial anion. Okay, a partial negative charge. And where are we going to get a partial negative charge from? A large difference in electronegativity. Okay? So a large difference in electronegativity would be a polar covalent bond. I could now go through and be like, which of these gets me a polar covalent bond? Water has a polar covalent bond. DMSO has one. Acetone has one. Acetic acid has one. Right? That's a lot of possibilities. Which one do you want to circle? Okay, we'll pick water. Your solvent choice is best described as. There are 3 categories that we can use for our solvents. Protic, which is now relevant for part C, means it's hydrogen bonding. Polar aprotic means, and then nonpolar means, so if I look at water, the best choice is protic. Defining the term, it's a hydrogen bonding solvent. Okay? What if you circled, because what ifs are always fun. Let's clear everything. What if you circled hexane? It says circle the solvent that you think would be best. That's pretty sketchy. It shouldn't be hexane. Did you describe it as nonpolar? And did you say it was London dispersion? I'm going to give you credit for those two because those two align with the answer choice you picked. Are you wrong? Yeah, but you're at least internally consistent within that system. Does that make sense? Should I drop points for that circle?
Yeah.
That's an interesting question. With what we have visible on the screen right now, okay, I would probably say yeah, except that if we scroll down a little bit, explain why you selected that solvent. Okay. So in this particular case, what I would probably do is accept any circling for that first one. Are you internally consistent? And then what's your explanation? And if you're going to tell me the hexane is going to do a better job at stabilizing that cation than any of the others, well, no, you're wrong. I don't think you can tell me anything that would make me go, yes, you're right. Which means you're going to lose 2 points here, but you then pick up the other points for being internally consistent with that information. Does that make sense? Why does water work as the best to stabilize the cation?
Throw back to one of the first questions we answered, the hydrogen bonding solvent can interact with dipole-dipole and electrostatic forces. So when we scroll up, we see that at first is dipole-dipole.
Yeah, keep going.
Uh,
Because right now, you haven't given me a reason to exclude DMSO.
However, as we see that the mechanism where the reaction occurred, it turns into an ionic
Okay.
structure,
Yeah.
right? proton, right? Protic.
Cool, water can donate a proton. Do I want a proton being donated to a positively charged thing?
To
Nope, that's a
a
positive
negatively
positive.
charged thing. The iodine.
I didn't ask about the iodide, I asked about the carbocation.
Carbon.
Flip it on its head. You're generating a
So the
positive
OH
hydrogen. What else are you generating?
An OH, a minus OH.
A negative oxygen. That negative oxygen can be used to stabilize the positive cation. Why do I want hydrogen bonding with water? That's a stronger dipole generated than the dipole between sulfur and oxygen. That's generating a larger negative. That larger negative is going to do a better job stabilizing the positive. That's why we would push the protic solvents, because the protic solvents have a stronger force. It's a stronger force because they have larger dipoles. So you had the right idea, you just looked at the wrong half of it. Make sense? Cool. Are we excited? Yes, okay. 1 out of 30, that's passing, right?